We see them launch all the time, right? These giant metal tubes just blasting off into the sky. But how do they actually do it? How do they conquer gravity and punch their way into space? Well, the answer comes down to a really simple principle of physics, but the story of how we first used it to talk to each other from orbit, that's where things get really interesting.
So, let's kick things off with a little bit of trivia. What do you think was the very first human voice ever broadcast from space? And I'm not talking about, some beeps or static. I mean an actual real voice sent from orbit all the way down to Earth. Take a guess.
Believe it or not, it was a Christmas message, a message of peace from the President of the United States at the time, Dwight D. Eisenhower. Just think about that for a second. One of the very first things we did with this mind-blowing technology was broadcast a message of goodwill to the entire planet from the stars.
Yeah, this all happened way back on December 18th, 1958. It was on a rocket that launched the world's very first communications satellite, which got the cool nickname the Talking Atlas. That single launch, that one mission, it basically kickstarted the entire satellite industry that we all depend on for, well, everything, from GPS to weather forecasts. But to get how that worked, we've got to look inside the rocket itself.
So, what is actually going on inside one of these giant tubes? I mean, it kind of looks like it's just one massive engine, but a rocket is really three critical systems all working together in perfect sync.
First up, you've got the rocket's body. The frame on the inside uses these incredibly strong but super lightweight metals, like titanium. And then the outer skin, that acts as a thermal shield, protecting everything inside from the insane heat you get when you're blasting through the atmosphere.
Okay, the first big system is the payload. And honestly, this is the whole point of the launch. It's the what that's being delivered to space. For that Talking Atlas rocket, the payload was a satellite. For other missions, it could be supplies for a space station, a deep space probe, or of course, a capsule carrying people.
Next, you have the guidance system. This is, for all intents and purposes, the rocket's brain. It's this super sophisticated mix of computers, sensors, and radar that are constantly crunching numbers and adjusting the flight path, making sure the rocket gets exactly where it's supposed to go.
And finally, we get to the powerhouse, the propulsion system. This is the big one. It's the engines and the gigantic fuel tanks that make up most of the rocket structure. In fact, get this. For a lot of rockets, over 90% of their entire weight at takeoff is just fuel. So, how does burning all that fuel create enough raw power to actually leave the planet?
Well, it all comes down to a surprisingly simple, kind of elegant law of physics, one you definitely learned about in school. The real genius is just how rockets apply it on such a massive scale.
I mean, this is the fundamental problem, right? How does an enormously heavy tube generate enough oomph to overcome Earth's incredibly powerful gravity and just escape?
The answer is all thanks to Sir Isaac Newton and his third law of motion. For every action, there is an equal and opposite reaction. That one single idea is the foundation of, well, all of rocketry.
So here's how that actually plays out in an engine. You can think of it like a superhero punching the ground to fly up into the air. The rocket burns its fuel, which creates a massive amount of hot gas. The action is blasting that gas down at incredible speed. And the equal and opposite reaction, well, that's a powerful force that pushes the rocket up. It is literally climbing into the sky on a pillar of its own exhaust. Wild, right?
But, a successful launch isn't just about raw power pointing straight up. If you've ever watched a full launch from start to finish, you might have noticed something a little weird about the rocket's path.
It's this maneuver they call the gravity turn. So for the first minute or so, the rocket goes straight up, full power. But then it starts to tilt, making this big arc. It doesn't just fly in a straight line all the way to space. So why the detour?
It's all about being smart and efficient. See, the goal isn't just to go up. The real goal is to achieve orbital velocity, which means going sideways so fast that you're constantly falling around the Earth. Just trying to fight gravity head-on is a huge waste of fuel, and it puts incredible stress on the rocket from air resistance. The gravity turn cleverly uses Earth's own gravity to help bend its path, building up that all-important sideways speed while saving a ton of fuel and minimizing stress.
To make that whole journey even easier, the rocket also sheds weight as it climbs. We call this stage separation. Once those huge first-stage boosters are out of fuel, they're just dropped, falling back into the ocean.
This makes the rest of the rocket way, way lighter and more efficient, allowing the next stage engines to push the payload the rest of the way into orbit.
When you really think about it, the rocket isn't even the point of the mission. It's just the most sophisticated, most powerful delivery vehicle we've ever built.
A rocket has one job, and one job only, to get its payload into space. That's it. Whether it's a satellite, a capsule, or a telescope, once that payload is on the right path, the rocket's work is done.
And that one simple job has completely changed everything for us. I mean, without these incredible metallic tubes, our entire understanding and exploration of the universe just wouldn't be possible. You know, that single talking Atlas rocket back in 1958, that was the start of something massive. Today, the space industry that's built on rocket technology is worth over $500 billion. It affects the GPS in your phone, the weather forecasts you watch every day, and even our ability to monitor the health of our own planet.
Which really just leaves us with one final fascinating question. For more than 60 years now, we've perfected the science of getting off our planet. So, now that we know how to leave, where will these incredible vehicles take us next?